In the second part of this module, we will look more in detail on the criteria for renewable energy site selections. We go hands-on in QGIS and build our first multi-criteria suitability map. This is useful to learn how to prepare, reclassify, and combine raster layers into a composite overlay. But first, let's do some preparation. You will need a couple of layers for these parts. These layers are typically mixed. Some are raster, some are vector. That's why it may be useful to convert everything to raster before moving on to reclassify each one, and finally applying the weighted overlay. So before moving on to QGIS, take a few minutes to make sure all these files are downloaded and organized well. Create a project folder and place the layers inside it. Let's start with QGIS and processing the renewable energy layers one by one, reclassifying, weighting, and combining them to build your first suitability map. First, consider the resource availability. For wind, this is usually the average wind speed at hub height, which influences greatly the kilowatt hours generated by the plant. For solar, the most important factor is the radiation. The more, the better, and we typically define a minimum threshold. To work with the layer, we will first need to download it and upload it in QGIS. Then, to combine the different layers, they need to speak the same language. This means reclassifying each raster to a common suitability. An alternative would be a normalization using a continuous scale. As told before, we will use 1 to 5. This allows us to compare and combine very different variables like wind speed, slope, and distance. For example, we can define wind speed above 8 meters per second as suitability 5, wind speed between 7 and 8 as suitability 4, and so on down to low values until suitability 1. We can do this with two tools in QGIS. First, the raster calculator using manual expressions, and second, the reclassify by table tool using a value mapping table. Let's use the raster calculator. For the wind layer, write an expression like discussed before that separates the areas according to the different suitability. Now we will do something similar for distance to infrastructure. Roads and transmission lines are crucial for building renewable energy projects. Sites close to them reduce cost for logistics and grid connection. We'll use proximity rasters for this and limit our analysis for this example for distance to major roads only. Regarding the distance, the closer, the higher the suitability. Again, we need to download the map with the roads in Italy. I've already done this, as you can see, and now we need to compute the minimum distance to major road infrastructure. To do that, we need to rasterize the road shapefile and create a distance raster. This is what you can see in the screen recording. Again, be careful with the coordinate reference system. Then you might invert the scale using this formula. Save the reclassified raster layers with clear file names to avoid confusion later. Now let's move on to topography. Slope and elevation impact construction costs and performance. Flat terrain is usually preferred. You can extract slope from a DEM, and very high slopes might then exclude a site from the analysis as construction and foundations become impractical. Therefore, we will first exclude all areas with a slope of more than 20% and then do an evaluation similar to the previous one with the remaining areas. The areas with slopes lower than 4% will receive the suitability value of 5 and then moving down this way. A very important factor to consider is the land use and the associated legal constraints. Not all areas are available for renewable energy development. Some areas have strong restrictions and won't be able to host a utility-scale wind farm. To consider this, we will need to exclude national parks, Natura 2000 zones, urban zones, and others. These can be included as binary masks, so 0 being excluded and 1 being allowed. For simplicity, let's exclude only national parks in our analysis. If you want to do a more holistic and precise investigation, you can apply the same concept to urban areas, rivers, lakes, and other unsuitable land types. These are usually vector layers, so polygons. To apply them to our raster-based analysis, we need to either use the clip raster by mask layer to remove them, or create a binary mask where 1 is allowed and 0 is forbidden, and then multiply it with the suitability layers. If you use a binary raster mask, multiply the wind suitability with a constraint mask in the raster calculator. Great! The major step is done. Having the layers ready and suitable takes some time. Now that everything is reclassified and constraints are applied, it's time to combine them using weights. The weights reflect how important each factor is in our decision. For example, wind can be a 40% factor, slope 30%, and the distance to road another 30%. As discussed earlier, selecting proper weights is the most critical step of multi-criteria assessment, and there is no right or wrong way to do it. But changing the factors can completely invert the results. These weights should add up to 1 and ideally reflect expert input, planning guidelines, or stakeholder priorities. You can adjust them in a sensitivity analysis. We are now at the point to finally combine the different layers. Again, let's use the raster calculator to apply the weights and build your composite map. Save the inputs as the suitability index file. This is the final composite suitability map. The values now range from low, which is unsuitable, to high, optimal, combining all the different criteria. In a final step, let's visualize the final result. Right-click on the raster, choose Properties, and then Symbology. And there you can apply a graduated color map, for example a green to red scale. You can use quantiles or natural breaks to classify the map into 5 levels, or stick with a graduated visualization. You can now interpret which areas are most suitable and where to prioritize further analysis. Try zooming into a region to inspect how slope, roads, and wind come together in the result. Great, we've built a weighted overlay model in QGIS.